In 1869, the railroad tycoon Cornelius Vanderbilt looked at a young inventor's plan and asked, essentially, whether anyone could seriously expect to stop a train with something as flimsy as air. It was a fair question. Air compresses, air leaks. Air seems like the wrong tool for a job that involves stopping hundreds of tons of moving steel. Cars stop with hydraulic fluid, a solid, incompressible column pushed through a sealed line, and it works great. But every train in the world still runs on air instead, and the actual reason has almost nothing to do with stopping power. Start with the man Vanderbilt was talking to. George Westinghouse patented an automatic air brake in April of 1869, barely in his 20s at the time, years before he'd go on to build an electrical empire that would put him in direct competition with Thomas Edison. His first version genuinely wasn't very good. It used what's called a straight air system. Air pressure pushed directly from the locomotive to apply the brakes on each car, one after another, all the way down the train. It worked when everything stayed connected, and Westinghouse proved it on a real demonstration run between Pittsburgh and Steubenville, Ohio, with a pump and tank rigged onto the lead locomotive, air lines run back to every trailing car, and a cylinder and piston fitted to each one. Skeptical railroad men rode along to watch it fail, expecting the whole demonstration to end in an embarrassing rollback. It didn't. But if a hose burst or a coupling failed anywhere along the train, the brakes on every car past that point simply died, along with the air pressure, at the exact moment they were needed most, right when the crew needed every ounce of stopping power the system could offer. A safety system that fails by doing nothing isn't really a safety system, no matter how well it works the rest of the time. Westinghouse knew it too, and by 1872 he'd redesigned the whole thing around a completely different idea. One that flips the entire logic of how the brakes fail, using the very same medium that had just failed him. Vanderbilt wasn't the only skeptic. Most of the industry assumed the same thing he did, that a gas thin enough to breathe couldn't possibly generate the mechanical force needed to stop a loaded freight train, and that assumption wasn't unreasonable on its face, given everything else in heavy industry at the time ran on steam pressure, steel cable, or brute muscle. Westinghouse's demonstration run answered the force question well enough to win early customers. It took the near disaster of his first design and 3 more years of redesign work to answer the harder question nobody had thought to ask yet. Not whether air could stop a train, but what happened when the system carrying that air failed halfway through a run. Here's the part that actually explains why air won out. In the redesigned system, air pressure doesn't apply the brakes, it holds them off. Every car carries its own small air tank, kept full and ready by a continuous pipe running the length of the train, charged and recharged by a compressor up on the locomotive that never really stops running while the train is moving. As long as that pipe stays pressurized, the brakes stay released. Drop the pressure, whether the engineer does it on purpose to slow the train or a coupling breaks and rips the whole pipe apart by accident, and the brakes apply automatically, on their own, without needing a single instruction to reach them. A train that breaks in half doesn't roll away out of control. It stops immediately on every single car, because losing pressure and stopping are literally the same event. That inversion is the actual answer to the question, and it's also exactly why hydraulic fluid was never a serious option for this job, no matter how much force it could theoretically deliver. A fail-safe system needs a medium whose natural, resting, do-nothing state is the safe one, and finding a working substance that already behaves that way, for free, without a single extra part, is rarer in engineering than it sounds. Air already wants to do that, without anyone having to design it into existence. Let it leak, and it simply returns to atmospheric pressure. The same air that's sitting outside the train anyway, free and unlimited and already there, no matter where in the country the train happens to break down. Build the brakes to release when pressure is present and apply when it's gone, and you've turned a plain physical fact about air into the entire safety system, with no extra parts required to make it fail in the right direction, no batteries to die, no backup generator to fail to start. Hydraulic fluid doesn't behave that way at all. A sealed hydraulic line holding pressure doesn't want to return to some harmless resting state if it springs a leak. It just loses fluid, and once that fluid is gone, it's actually gone. Not sitting in the atmosphere, waiting to be recompressed for free the moment a compressor kicks back on. Somebody has to haul in more of it, filter it, bleed the air bubbles back out of the lines, and refill every reservoir by hand. A maintenance job that has nothing to do with the actual mechanics of braking and everything to do with keeping the working fluid itself intact, day after day, car after car. Multiply that across dozens of cars getting coupled and uncoupled in a rail yard every single day, each connection a place where fluid could leak out and contaminate the couplers, and the practical case against hydraulics falls apart before you even get to the question of whether it could be made fail-safe at all. There's a coupling problem underneath all of this too, and it's a purely mechanical one, separate from anything about safety logic, though it points toward the exact same conclusion from a completely different direction. Air hoses between rail cars use a simple fitting called a glad hand, designed to connect and disconnect quickly, tolerate a bit of misalignment, and survive a small leak without any real consequence, since a little lost air costs nothing and refills itself the moment the compressor runs again. Workers coupling cars together don't need precision or special training to make that connection reliable, which matters enormously in an industry that couples and uncouples cars by the thousands every single day, all across the country, in every kind of weather. A hydraulic connector carrying incompressible fluid under real pressure has none of that forgiveness built in. Every connection has to seal essentially perfectly, every time, in freight yards where cars get slammed together and pulled apart constantly, in weather ranging from desert heat to sub-zero cold that would stiffen and crack seals never designed for that kind of daily abuse, on schedules that don't pause for a single one of those connections to be inspected by hand. Air tolerates sloppiness that would make a hydraulic system leak fluid all over the tracks. None of this comes free though, and the cost is baked into the same compressibility that makes the whole system work. Because air compresses, a pressure change doesn't travel down the brake pipe instantly, it moves as a wave, at roughly 150 meters a second. Fast enough to feel instant on a short train, but not fast enough to actually be instant on a train that might stretch well past a mile long. On a 100-car train, the front cars start braking measurably before the rear cars do, a gap that's tiny in isolation but very real when you're talking about tens of thousands of tons, all trying to slow down together at slightly different moments, spread across more than a mile of track. If that timing gets uneven enough, the slack between all those couplers can bunch up violently in what railroaders call a run-in, a genuine derailment risk that traces directly back to the same compressibility that makes the fail-safe design possible in the first place. The same property that saves the train also has to be managed carefully every single trip by crews who understand exactly why it behaves that way. That same limitation shows up on ordinary grades, not just emergencies, and it's a problem every engineer running mountain routes has to plan around before the trip even starts. Taking a loaded train down a long descent is far more complicated than easing off a car's brake pedal a little at a time. Air brakes on a long train can't be released gradually the way a hydraulic system in a car can, a limitation that has nothing to do with skill and everything to do with the physical medium carrying the command. No fine adjustment, just degrees of on. Try to raise the pipe pressure just slightly to loosen the brakes a touch, and that small signal decays as it travels, fading out almost completely by around 600 meters and never reaching the rear of a long train at all, no matter how carefully the engineer times the adjustment. Engineers running loaded trains down mountain grades have to work around a control system that's fundamentally coarser than what a car driver takes for granted every single day, planning their braking well ahead of a curve instead of reacting to it the way a driver casually taps a pedal. That same fail toward safe logic got reused for an entirely different problem decades later, one Westinghouse never had to think about because the technology it addresses didn't exist yet. Modern locomotives carry something called a penalty brake, which automatically dumps air pressure and triggers a full stop if the train exceeds a speed limit, if the engineer fails to respond to a signal, or if a safety system detects the crew isn't reacting the way it should, catching exactly the kind of human lapse that Westinghouse's original design was never built to think about. It isn't a separate invention, it's the exact same 1872 idea, repurposed for a century's worth of new safety requirements nobody could have predicted at the time, wired into technology. Westinghouse never lived to see, drop the pressure on purpose, for any reason at all, safety-related or not, and the brakes apply themselves without anyone needing to build a new mechanism from scratch. One elegant physical trick, reused for problems the original inventor never anticipated, solving them without requiring a single new law of physics, just a new application of the one he'd already proven worked. Modern railroads haven't thrown the whole idea out to fix that delay. They've layered something new on top of it instead. Electronically controlled pneumatic brakes add an electric signal running alongside the traditional air pipe, so every car on the train gets the command to brake at effectively the same instant, using wires instead of a pressure wave that has to physically travel the length of the train, car by car, second by second, the way it's had to for 150 years. The air still does the actual work of pushing the brake shoe against the wheel, and the air still fails safe if something goes wrong, exactly the way it has since 1872. The electric layer just fixes the one real weakness air always had: how long it takes news to travel down a very long pipe. Everything else about the original logic stays exactly the same, untouched for a century and a half of railroading, through steam, through diesel, through every generation of locomotive built since. So the actual reason trains use air instead of hydraulics was never really about which one pushes harder. It's about which one fails in the right direction on its own, using nothing but ordinary physics, at every single coupling on a train that might be a mile long and running through weather no engineer controls. Vanderbilt was thinking about force. Westinghouse ended up solving something else entirely, a problem nobody had even framed as a real question. Yet, in 1869, back when force was the only variable anyone thought to measure, air was the weaker choice by every measure Vanderbilt would have cared about at the time, judged purely on raw stopping force, the exact metric that mattered to him. It turned out to be the safer one for exactly the same reason, a century and a half of railroading later, and counting. So here's the question worth sitting with. When the fragile-looking option turns out to be the one nature is willing to fail safely for free, was it ever really the weaker choice at all?